The first sign would not be a sound, but a stillness. The sun would hang in the sky longer than it should. Shadows would stop their quiet march across walls and fields. The wind, the oceans, the air above every continent would remember a motion the ground beneath them had suddenly lost. In that strange moment, Earth would still look like Earth. Blue oceans, white clouds, familiar continents, and yet the oldest rhythm in our lives would already be gone. We rarely think about the fact that our world is spinning. We do not feel it in our bones. We do not hear it in the night. But every sunrise, every weather pattern, every ocean current, and every ordinary day depends on that invisible turning. Near the equator, the surface of Earth moves fastest. The atmosphere moves with it. The seas move with it. Entire systems of heat, wind, and water are shaped by it. Remove that motion, and the planet does not simply pause. It begins to change in ways both violent and deeply unfamiliar. The science behind this is not fantasy. Earth really does rotate once every 24 hours. That rotation helps drive the circulation of the atmosphere, influences the movement of the oceans, and creates the cycle of day and night that governs life from forests to coral reefs to human sleep itself. A sudden stop is not something nature is expected to do, and no evidence suggests it ever has. But asking the question is still meaningful, because the answer can be explored through real physics, real climate science, and what we already know about motion, energy, heat, air, and water. So tonight, the question is simple, even if the consequences are immense. What if Earth stopped spinning? Not vanished, not shattered, not knocked out of orbit, just stopped rotating on its axis while continuing its long path around the sun. What would happen in the first second, the first hour, the first year? Which parts of the planet would be destroyed first? What would become of the oceans, the sky, the climate, and the thin band of life that depends on regular light and darkness? This is worth exploring because it reveals something easy to forget. The stability of our world is not permanent or passive. It is built on motion. And by following that idea carefully, step by step, we can trace a believable path from the immediate shock to the long aftermath. If you enjoy these quiet journeys into science and deep time and the hidden mechanics of our planet, take a moment to like the video, subscribe, and tell me in the comments where you are watching from tonight. Now dim the lights, settle in, breathe slowly, and let the noise of the modern world drift a little farther away. As the room grows softer and darker, we can begin to imagine a planet that keeps moving through space even after it forgets how to turn. Imagine the second after it happens. The continents are still beneath the clouds. The mountains have not vanished. The seas have not boiled away. From space, the planet looks almost unchanged, as if nothing dramatic has occurred at all. But along the surface, the old agreement between the ground, the air, and the oceans has been broken. The Earth has stopped. Almost everything else is still trying to go on. That is the first idea to hold in the mind, because it explains almost everything that follows. A sudden stop of the solid planet would not feel like a gentle pause. It would feel like the world beneath you had been removed from its own motion, while your body, the atmosphere, and the seas still remembered it. We do not feel Earth rotating now because everything around us shares that movement. The floor under our feet, the buildings around us, the trees outside the window, the clouds above the roof, and the blood moving quietly through the body all travel together. Uniform motion disappears into normal life. Only change makes itself known. Only when that shared motion is interrupted does the silence break. At the equator, the surface of Earth moves eastward at roughly 1,670 kilometers per hour. That is more than enough speed to turn the ordinary world into something unrecognizable if it were suddenly taken away from the ground, but not from the things resting on it. At higher latitudes, that speed is lower because each circle of rotation becomes smaller as it approaches the poles. Near the poles, the eastward motion becomes small enough that the immediate mechanical violence would be much less severe. The difference matters. This would not be a single disaster distributed evenly around the globe. It would be a gradient of catastrophe. Worst where the planet had been moving fastest, less severe where the daily turning had always been slowest. For a brief and terrible interval, the surface would stop being a place and become a collision. Everything, not deeply fixed into bedrock, would lurch eastward relative to the ground. People, vehicles, furniture, loose stone, topsoil, the contents of homes and factories, the surface waters of lakes and rivers, and much of the lower atmosphere would continue moving. Some things would be torn apart instantly. Others would become projectiles. Great cities, built under the assumption of a stable world, would meet a physics they were never meant to resist. Towers would fail under lateral stress. Power lines, pipelines, bridges, and ports would be struck not by one clean blow, but by a moving wall of air, debris, and water. In many regions, survival in the first minutes would depend less on planning than on geography and pure chance. The image most people imagine first is often the wrong one. It is easy to picture the entire planet shattering, continents breaking loose, mountains flying sideways, or the atmosphere vanishing in an instant. Those visions belong more to spectacle than to careful reasoning. The crust would not simply peel away, because the scenario begins by assuming the solid Earth somehow has already stopped as one body. The atmosphere would not instantly escape to space because Earth would still have its gravity. The oceans would not rise all at once into one global wall of water. What would happen instead is more complicated and in some ways more unsettling because it unfolds according to real principles. Motion would remain where motion already existed. Air would keep moving. Water would keep moving. Loose bodies would keep moving. The damage would come not from fantasy, but from inertia. If you stood on the equator at the impossible instant of the stop, there would be no time to understand it. There would only be acceleration relative to the ground, the sensation of being thrown eastward, and then whatever lay in that direction. Even if the body could survive the initial force, the surrounding environment would become lethal almost immediately. Air itself would become a weapon. The winds that today circled the globe as part of familiar weather would be replaced by a far more violent inheritance, an atmosphere still carrying the eastward speed of a rotating world over a surface that no longer rotated beneath it. At the equator, that relative motion would be faster than the cruising speed of many aircraft. And because the atmosphere is not a single rigid shell, but a deep, turbulent fluid, those first hours would not be one simple blast. They would be a vast, chaotic redistribution of momentum. The lower atmosphere would grind across mountains, forests, cities, and deserts. Coastlines would be stripped by spray and debris. Sand,
glass, splinters of concrete, uprooted trees, and parts of buildings would all be taken up into the flow. Places that survived the first physical jolt would then face winds of extraordinary intensity. Even regions away from the equator, where the inherited eastward speed was smaller, would still face storms beyond modern experience. The exact pattern would be difficult to predict in detail,
because the real atmosphere is shaped by topography, temperature, moisture, and pressure. But the broad fact is clear. A suddenly non-rotating Earth would initially possess a rotating atmosphere, and the process of slowing that atmosphere against the surface would be catastrophic. It helps to picture the scale of the thing. Earth's atmosphere is not a thin decoration painted on the globe. It is a vast envelope of moving gas, extending upward in layers, carrying heat from one region to another, rising and sinking, condensing into cloud, pouring as rain, and bending around mountain ranges and ocean basins. To change its motion abruptly is to disturb one of the largest fluid systems on the planet. In daily life, the atmosphere seems weightless, but it has mass, enormous mass. That mass, moving at great speed, would not stop politely. Friction with the surface would gradually drain its motion away, but friction itself would be part of the violence, heating the lower air, intensifying turbulence, driving pressure differences, and producing a world of wind unlike anything in recorded history. The oceans would be slower to tell their story, but no less destructive. Surface water near the equator also carries the planet's rotational speed. Unlike a small bowl of water on a stopped table, the sea is deep, heavy, and only partly constrained by coastlines. Once the ground stopped beneath it, the oceans would continue their eastward motion, surging against continents and across shallow shelves. Coastal regions would become the meeting place of two disasters at once, a moving atmosphere above and moving water below. Harbors, river mouths, low islands, deltas, and continental margins would be struck hard. The first great pulses of water would not be neat textbook waves spreading evenly around the globe. They would be confused, amplified by underwater shape, redirected by bays and peninsulas, and transformed by the collision between moving sea and suddenly motionless land. Some inland regions might, at first, seem safer by comparison, but safety would be a relative word. The farther one moved from the coasts, the less immediate the danger from ocean surges. Yet, inland landscapes would still face intense winds, debris, and the breakdown of every interconnected system that supports modern life. Roads would be blocked, electrical grids would fail, communications would collapse, water treatment plants, hospitals, fuel supplies, and food distribution networks would be disrupted in ways difficult to exaggerate. In many cities, the greatest threat after the first atmospheric assault might not be a single dramatic event, but the rapid transformation of dense human environments into places without clean water, reliable shelter, or medical care. Near the poles, the story would begin differently. Because the rotational speed there is so much lower, the immediate eastward inertia of loose bodies and air would be far less dramatic. A person standing close to the rotational axis would not be flung sideways at equatorial speed because that speed does not exist there. The atmosphere would still be disturbed globally, and the loss of normal circulation would still matter, but the first mechanical shock would be much less extreme. That does not mean the poles would be safe in the long term. It means only that the opening minutes and hours would be kinder there than almost anywhere else on Earth. In a world where most maps of risk would need to be redrawn at once, proximity to the poles
could briefly become an unexpected advantage. There is another part of the old rotational world that would begin to fade, though more quietly. Today, Earth is slightly wider at the equator than from pole to pole. This bulging shape exists because rotation creates an outward effect strongest at low latitudes. If Earth stopped rotating, that effect would disappear. The planet would not instantly change shape like a released spring, but over longer spans of time,
The oceans would respond to the altered balance. Water would tend to migrate away from the equatorial bulge and toward the poles. That long adjustment belongs more to the slower future than to the first day. Yet, even in the beginning, the consequences of rotation are already present in the geography of the crisis. The modern world is not only living on a spinning globe, it is living on a globe whose very shape has been slightly molded by that spin. For the moment, though, shape matters less than speed. The most immediate question is what the human senses would encounter. The sky would not suddenly turn strange in the first few minutes. The sun would still be where it had been a moment earlier, and the clouds, if there were clouds overhead, might still look familiar for a breath or two before their motion relative to the surface began to reveal the new reality. What would seem impossible is the air. A roaring, grinding atmosphere, stronger than any natural storm most people have ever imagined, would arrive with little warning, because the warning would be the event itself. In exposed places, breathing would become difficult. In urban areas, the first cascade of failing structures would feed the flow with more debris. In forests, trunks would snap or uproot. On open water, vessels of every size would face conditions beyond ordinary navigation. The geography of the equatorial belt would be especially tragic, because so many of Earth's warm, densely populated and biologically rich regions lie there or nearby. Tropical coastlines, island chains, major ports, fertile deltas, and vast cities would all sit close to the zone where inherited speed was greatest. Some of the most productive agricultural lands on Earth are low and coastal. Many of the busiest shipping routes connect exactly the regions that would be hardest hit. Coral reefs, mangroves, estuaries, and shallow continental seas, already delicate in their own ways, would endure a level of mechanical disruption few ecosystems could survive intact. The disaster would not distinguish between human infrastructure and ancient habitats. It would erase both with equal indifference. Even away from the equator, mountains would complicate the atmospheric response. Air forced across major ranges would accelerate, descend, rise, and break into severe turbulence. Valleys could become channels for focused winds. Leeward sides might see chaotic eddies and pressure contrasts. High plateaus that seemed removed from ocean danger might still face violent atmospheric conditions shaped by terrain. Yet those same elevated interiors could later become valuable refuges, not because they escaped damage altogether, but because they stood above coastal inundation and away from the worst of the first oceanic surges. Altitude has always been a kind of distance from the sea. On a stopped Earth, that simple fact would suddenly matter much more than it does today. The seas themselves would not only slam coastlines and then retreat, they would continue to redistribute. The first movements might resemble immense eastward surges, but the real ocean is a connected system with basins, ridges, shelves, trenches, and rotating circulations already embedded within it. Once the old rotational balance vanished, water would begin a complex response. Some shorelines would be struck repeatedly. Enclosed seas and gulfs could amplify destructive oscillations.
Large lakes would generate their own internal surges. River systems might reverse locally under sudden coastal pressure. Sediment would be torn up and carried far from its previous resting places. Ports and estuaries would fill with debris and mud. The map of coastlines would begin changing almost immediately, even before the slower, long-term redistribution of the oceans had time to appear. In this early phase, temperature would not yet be the dominant story. That belongs to the days, weeks, and months that follow,
when the absence of ordinary day and night begins to reshape climate itself. During the first hours, the inherited heat of the atmosphere and oceans would still resemble the world that existed moments before. Tropical air would still be warm, polar air would still be cold. The sun would still illuminate roughly the same hemisphere as it had just before the stop. But already, something deeper would be changing. The clock by which the atmosphere had long organized its rising columns of warm air and descending masses of cool air had been broken. Weather, as a daily pattern, would be wounded before it had fully realized what had happened. That is important because the familiar weather of Earth is not random. It is the product of solar heating, moisture, topography, and rotation working together. Rotation shapes the great circulation cells and helps organize winds into the patterns that mariners, farmers, and meteorologists have studied for centuries. Remove rotation, and the old system does not merely weaken, it must become something else. In the first violent hours after the stop, that larger transformation would still be hidden inside the chaos of inertia. But the hidden transformation is what gives the initial disaster its larger meaning. This is not a storm that passes and leaves the same Earth behind. It is the first phase of a planet changing its entire behavior. If we slow the scene down in the imagination, there are countless local tragedies nested inside that planetary shift. A commuter train in a tropical city, a cargo ship entering harbor, a family in a coastal apartment tower, a herd of animals on open savanna, a forest canopy alive with birds and insects, a research station on an island reef. Each exists at a different point along the gradient of speed and exposure. Each experiences not an abstract planetary event, but a specific encounter with air, motion, structure, and terrain. This matters because disasters often become unreal when seen only at global scale. Yet the stopped Earth would be both global and local. The great physical laws would express themselves through streets, shorelines, valleys, rooftops, and bodies. Some modern structures would endure better than others. Low, reinforced buildings, deeply anchored into bedrock, might survive where taller or lighter construction failed. Underground shelters could provide protection from debris and wind, though not from every danger that followed. Aircraft already in flight would face conditions far beyond normal aviation, especially at lower altitudes where atmospheric turbulence and shifting winds would be extreme. Large ships in deep ocean might survive the first moments better than vessels near coasts, but survival would still be uncertain once the ocean began redistributing its momentum across basins and continental edges. There would be no universal safe technology, because the event would not be one problem. It would be many problems arriving at once. Animals, too, would experience the opening phase unevenly. Burrowing species might outlast the first winds. Polar and subpolar creatures would initially fare better than tropical coastal life. Forest animals would face falling trees and airborne debris. Migratory birds would lose the atmosphere they knew. Marine life near shore would suffer from violent water movement, suspended sediment, and coastal destruction,
while deep ocean organisms might remain physically untouched for longer, protected by distance and depth from the immediate surface chaos. It is one of the strange features of planetary catastrophes that remoteness becomes a form of resilience. Places and organisms far from the visible center of the drama may endure longest, not because they are stronger, but because they are spared the first direct blow. There is also the question of fire. In heavily built human regions, the combination of damaged electrical systems,
Ruptured fuel lines, and debris could ignite many local fires. Strong winds would then spread them quickly where combustible material remained. Yet, in some places, the same violence would remove fuel, saturate the ground with water, or simply prevent flame from holding. So, the first burning world would be patchy rather than uniform, intense in industrial zones, urban corridors, and drought-prone landscapes, less significant in flooded coasts or blasted, stripped terrain. Again, the real picture is more complex than one grand cinematic image. The stopped Earth would not wear one expression, it would wear many, all at once. And while human attention would naturally focus on the visible assault of air and sea, another invisible process would already be underway within every social system. Modern civilization is built upon continuity. It assumes that roads stay where they are, ports remain usable, grids stay connected, satellites communicate, schedules hold, and food can travel from one region to another. A disaster of ordinary scale disrupts some of those assumptions, regionally and temporarily. The stopping of Earth would disrupt nearly all of them, globally and immediately. Even places spared the worst physical damage would inherit the consequences of worldwide interruption. Fuel scarcity, medical scarcity, communication breakdown, and the collapse of coordinated supply would become as decisive as the winds themselves. It is worth pausing over how quickly the ordinary meaning of distance would change. In the modern world, a city far inland may feel secure from the sea, while a remote polar outpost feels isolated and vulnerable. On a stopped Earth, those intuitions could reverse. Distance from the equatorial coasts might become life-preserving. Nearness to the poles might become an unexpected advantage. Harsh climates that once discouraged dense settlement could briefly become relatively stable compared with the ruined belts of low latitude. Some of the places least central to the old human world could become the anchors of the new one, at least for a time. Geography would not only determine destruction, it would determine the first map of possible survival. To understand why low latitudes would suffer so much more, it helps to return to the geometry of rotation itself. Every point on Earth takes 24 hours to complete one spin, but not every point travels the same distance during that time. At the equator, the path is longest. At the poles, there is almost no path at all, only a turn around the axis. That is why a sudden stop produces such different immediate effects. The inherited motion is a stored memory of distance covered in one day. Near the equator, that memory is vast. Near the poles, it is small. A stopped Earth is, in this sense, not one experiment, but many, layered together by latitude. The first day would therefore divide the planet into broad zones. In the equatorial and tropical belts, the opening violence of atmosphere and moving surface waters would be overwhelming. In the mid-latitudes, the shock would remain severe, though less absolute. In polar regions, the first mechanical effects would be comparatively limited, though not trivial, and the later climatic consequences would still loom.
Coasts almost everywhere would be more dangerous than interiors. Lowlands would generally be worse than uplands. Islands would be especially exposed, depending on latitude and terrain. Dense urban corridors would face cascading failures. Sparse, cold, or mountainous regions might hold together a little longer. The map of habitability would begin redrawing itself at once. All of this remains within the realm of plausibility because it begins from known physical truths. The numbers may vary depending on assumptions about how abruptly the stop occurs and how the atmosphere responds in detail, but the general principles do not. Rotation gives the surface speed. Inertia preserves that motion in air,
Water and loose bodies. Friction and collision convert motion into destruction, turbulence, and heat. Latitude controls the severity of the initial inherited speed. Coastlines amplify the meeting between moving ocean and motionless land. None of this requires speculative geology or imaginary energy sources beyond the impossible act of stopping the planet in the first place. Once that impossibility is granted, the consequences follow from familiar rules. There is a temptation in any scenario this large to imagine a single cinematic frame that explains everything. But the reality would be distributed through thousands of physical interactions happening at different scales. In one place, the decisive factor would be the speed of the wind. In another, it would be the angle of a coastline. In another, the height of surrounding terrain. In another still, it would be whether shelter happened to be below ground rather than above it. A stopped Earth would not produce one uniform apocalypse rolling neatly across the globe. It would produce countless local encounters between the old moving world and the new motionless surface, some lasting seconds, some lasting hours, each shaped by the details of place. Consider rivers. We usually think of rivers as responding to gravity alone, flowing downhill according to the slope of the land. That would still be true in the long run, but the first hours would be governed by momentum and by whatever happened where the rivers met the sea. In great deltas, estuaries, and tidal channels, the sudden movement of ocean water against the coast could force salt water inland with tremendous violence. River mouths could become zones of collision where floodwater, debris, and marine surges met head-on. Even far upstream, the consequences of coastal disruption would travel through the system. Sediment loads would rise, channels would be choked, banks would fail. Barges, bridges, levees, pumps, and intakes would all face conditions outside design limits. The rivers themselves would survive. Human use of them might not. Large lakes would have their own version of the same problem. Though smaller than oceans, they are still vast bodies of water with inertia. A sudden stop of the ground could set them sloshing with destructive force, especially where shorelines are shallow or enclosed. The first movements might resemble gigantic seiches, long-standing oscillations of water driven across a basin. Waterfront cities, marinas, industrial zones, and low shorelines around inland lakes could be struck hard, even hundreds or thousands of kilometers from the nearest ocean. The popular image of coastal catastrophe would therefore be incomplete. Water stored within continents would also become dangerous, not because it wished to leave the basin forever, but because, in the first hours, it would still be adjusting to a broken planetary motion. The air would tell a similar story, in layers. Near the surface, friction with land and obstacles would begin draining momentum quickly, though violently. Higher up, portions of the atmosphere could preserve more of their old eastward speed for longer. That difference would create vertical shear, one layer of air moving against another, feeding turbulence and strange pressure patterns.
The sky would not become calm once the first blast had passed. Instead, many regions would enter an unstable interval in which the inherited atmosphere and the newly forming circulation tried to occupy the same planet at the same time. That kind of instability is hard to visualize because there is no close modern equivalent. Hurricanes, derechos, jet streams, and dust storms each show one piece of the behavior, but the stopped Earth would combine familiar pieces into something globally unfamiliar. As the lower atmosphere lost speed through friction, some of its kinetic energy would be transformed into heat.
That does not mean the whole sky would burst into flame, or the air would instantly become unbreathable everywhere. But it does mean the first atmospheric phase would not be only mechanical. There would also be local heating, compression in descending flows, and the thermal consequences of dust, smoke, moisture, and violent mixing. In dry landscapes, airborne dust could travel in immense curtains, reducing visibility and adding abrasion to already destructive winds. In wet coastal zones, salt spray would be carried far inland. In cold regions, blowing snow and ice crystals could scour exposed surfaces. The character of the moving air would change from place to place, yet the underlying cause would be the same: an atmosphere trying to preserve a motion the Earth below it no longer shared. For human beings, one of the cruelest features of the event would be how little warning any ordinary person would have. Earthquakes sometimes offer seconds. Storms offer hours or days. Tsunamis, in certain circumstances, may offer a narrow chance of escape. But if the planet simply stopped rotating, there would be no separate precursor accessible to daily life. There would only be the event itself, and the consequences that began almost instantly. Whatever safety existed would therefore depend strongly on where a person already was when the world changed. A mountaintop observatory near high latitude might become a better refuge than a major hospital near the equator. A remote research station on stable ground could fare better than a wealthy coastal metropolis. This reversal of expected security is part of what makes the scenario so unsettling. It strips away many of the assumptions by which modern life measures preparedness. The architecture of vulnerability would extend below the surface as well. Underground spaces might protect from debris and wind, yet only if they were structurally sound, dry, and supplied. Subway systems in coastal cities could flood. Mines and tunnels in unstable ground could fail. Basements in urban centers might become traps if surrounding buildings collapsed or if water surged in. Caves in upland interiors could provide shelter, but only to those able to reach them before conditions became impossible. Even shelter on a stopped Earth would become geographical rather than merely technological. The old confidence that reinforced concrete, steel, and glass could master any environment would weaken quickly. The strongest refuge might be ancient terrain itself: bedrock, height, remoteness, and distance from the sea. The role of latitude would also affect human memory of the event. If any global civilization remained capable of sharing testimony afterward, accounts from different regions would sound as though they described different planets. One witness might speak of winds strong enough to erase coastlines. Another might describe a severe but survivable shock, followed by a long period of disorientation. Another, from near the axis, might report that the first day seemed less like immediate destruction and more like the beginning of a vast, incomprehensible emergency. This matters because it reminds us that planetary events are always filtered through local experience. Science unifies them under one explanation, but lived reality breaks them into regional worlds.
There is an additional subtlety in the immediate geography of danger. East-facing barriers and coastlines could experience the inherited motion differently from west-facing ones. Mountain chains would not just stand in the way of the moving air, they would shape where pressure built, where downslope winds accelerated, where moisture condensed, and where debris was focused. In some enclosed basins, the very terrain that offered protection from the sea might concentrate atmospheric violence. In others, terrain might break the force of the wind enough to create temporary shelters. Similar complexity would emerge along coasts,
where the angle of a shoreline relative to the moving water and air could determine whether a place was struck directly, partly shielded, or transformed into a funnel for destruction. The first map of survival would be written in contours and coastlines long before it was written in politics. Across the tropics, the biosphere would begin to absorb damage at a scale difficult to overstate. Rainforests depend on the circulation of moisture, on regular light, on intact canopies, and on a climatic stability that feels almost eternal when viewed through a human lifespan. But those forests are physically vulnerable to extreme wind. Once the canopy breaks, the forest beneath is exposed to heat, drying, and erosion in ways it was never meant to endure. Mangrove belts, which normally buffer coasts from storms, would themselves be torn apart by the unprecedented energy of moving water and air. Coral reefs would be shattered where waves and sediment plowed across shallow seas. Seabirds, insects, amphibians, river fish, and pollinating animals would all be caught in a crisis that was mechanical before it became climatic. Much of the living richness of low latitudes would be damaged before the longer, slower challenge of a changed sky had even begun. In temperate regions, the immediate ecological picture would be different, but not gentle. Agricultural plains would lose topsoil to wind in exposed areas. Orchards and forests would be broken or stripped. Reservoir systems could be compromised. Livestock would be exposed not only to the atmosphere, but to the collapse of fencing, barns, water systems, and transport routes. The modern food system relies on refrigeration, power, stable roads, and coordinated movement. Even if fields remained physically intact in some areas, the chain connecting food to people would fracture. This is one reason the first day cannot be understood only as a physical event. It would be the opening act of a food, water, and shelter crisis, reaching far beyond the zones of direct impact. This uncertainty would shape movement. In the first hours, large population flows might begin from coasts, floodplains, and unstable urban centers, but movement itself would be dangerous. Roads could be blocked by collapsed structures, downed lines, debris, fire, and flooding. Fuel would be scarce or inaccessible. Aircraft would be unreliable. Ports would be damaged. Even if survivors understood that high ground, inland distance, and higher latitude offered relative advantages, reaching such places would not be simple. The stopped Earth would not only change which places were desirable, it would make travel between places vastly harder. In this sense, geography would become destiny again, in a way the modern world had partly forgotten. Not every danger would arise from movement. Some would arise from sudden stillness. Rotating weather systems today are organized by forces that depend on Earth's spin. Once the immediate inertial phase weakened, winds in some regions could collapse temporarily before new patterns emerged. Coastal waters, after a first surge, might withdraw strangely before returning. Smoke could hang over damaged landscapes.
Dust could settle into a heavy atmospheric haze. In urban ruins, nights, at least in the old sense of the word, might still come at first, bringing darkness over places where power no longer existed. The absence of familiar human noise, traffic, machines, conversation, electrical hum, could become one of the most haunting features of the first surviving evening. The old world would not only be destroyed, it would be abruptly absent. For the first survivors, though, abstraction would come later. The opening concern would be simple and ancient. Where is shelter? Where is water? Where is high ground? Where is fire? Where are others? In some places, communities might gather quickly around naturally protected locations, caves, basements on stable uplands,
interior valleys shielded from the first atmospheric force, polar or subpolar settlements where the inherited speed had been lower from the start. In other places, especially where coast, heat, and population density combined, organized survival would be much harder. The event would strip humanity down to very old priorities, even while unfolding on a planetary scale. Yet even then, the sky would keep offering clues that the event was becoming something larger than a day of violence. The sun would not race onward in the familiar arc, because the familiar arc was tied to Earth's spin. At first, few would have the leisure to notice, but slowly, in the hours after the first great shocks, people would realize that the light seemed wrong, too fixed, too slow. Shadows would linger beyond their time. The normal expectation that the sky would carry the day forward would weaken. This subtle change would matter psychologically as much as physically. Human beings are deeply tuned to daily light. To lose the confidence of sunrise and sunset is to lose one of the oldest rhythms by which the mind orients itself. In that sense, the first day would end twice. It would end once as a period of immediate mechanical catastrophe, when the winds and waters finally spent enough of their inherited motion for scattered regions to breathe again. And it would end a second time as a period in history, when survivors understood that the disaster was not a storm to recover from, but the beginning of a new planetary order. The world they had known depended on rotation not only for physical stability, but for time itself as lived by bodies and ecosystems. Without that turning, every map, every schedule, every migration, every harvest, every sleep cycle, every coastal current, and every afternoon breeze belonged to a vanished order. What came next would not announce itself with the noise of impact. It would emerge gradually, like a truth noticed too late. The hemisphere facing the sun for too long would begin to hold its heat. The opposite side would begin a descent into prolonged darkness. Between them, a narrow belt would acquire a strange importance. The first catastrophe had been about stored motion. The next would be about stored light, stored heat, and the slow reorganization of air and ocean around a world that no longer turned. Circadian disruption would reach beyond mood and sleep. In humans and many animals, internal clocks are linked to patterns of hormone release, immune function, digestion, reproduction, and cognition. Artificial light can disturb these systems even today, which is why shift work and chronic jet lag carry physiological costs. On a stopped Earth, the sky itself would become a source of chronic desynchronization. On the day side, endless brightness would make rest difficult without shelter and deliberate darkness. On the night side, absence of sunlight would blunt or scramble the signals that normally tell the body when to wake, eat, and sleep. Communities able to survive physically
would still need to build time by hand, creating regular periods of light and darkness indoors to preserve health. Marine chemistry would begin to drift away from familiar patterns. Warm water holds less dissolved oxygen than cold water, so some overheated dayside seas could become harder for marine animals to breathe, especially if stratification reduced mixing between surface and deeper water. In darkness, cooling would increase oxygen solubility, but that would not automatically create healthy conditions if surface productivity collapsed and food webs unraveled. Places where deep water rose to the surface could become briefly rich in nutrients. Others might turn stagnant beneath persistent layers. Estuaries, already damaged by the first movements of the ocean, would be especially vulnerable because they depend on delicate balances between fresh water, salt water, tides, sediment,
and biological productivity. The stopped Earth would disturb every one of those balances at once. The cryosphere, too, would become a major actor in the new climate. Snow and ice are not passive decorations of the cold. They are reflective surfaces, reservoirs of fresh water, and insulators that separate air from soil or ocean. On the dark side, expanding snow cover would brighten the landscape for the eventual return of sunlight, making it harder for the surface to warm once illumination came back. Thickening sea ice would reduce evaporation from the water below, changing the moisture available to the atmosphere. Glaciers, nourished by prolonged cold, could begin advancing in some regions, even as mountain ice vanished on the long day side. Earth would become a planet of opposite cryospheres, one melting back, the other spreading outward, both linked to the same lost rotation. There is also the matter of storms. Some of the most powerful storms on modern Earth, including hurricanes and typhoons, depend on rotation to acquire and maintain their spinning structure. Without the Coriolis effect, those familiar rotating giants would not form in the same way. But the disappearance of one storm type would not mean a gentler atmosphere. Non-rotating worlds can still produce intense convection, towering cloud systems, straight-line wind events, and powerful thermal circulations. On a stopped Earth, storms might become less like spirals on a weather map and more like vast migrating walls and clusters driven by the contrast between overheated and overcooled regions. The aesthetic would change. The danger would remain. At a planetary scale, the carbon cycle would also begin to feel the shock. Forest dieback, phytoplankton collapse in some regions, wildfire in damaged landscapes, and the decomposition of dead biomass would all alter exchanges of carbon dioxide and methane between the surface and atmosphere. Wetlands that dried on the bright side could release carbon long stored in soils. Frozen regions on the dark side might lock some material away, while others could trap and preserve it only temporarily. These changes would matter because greenhouse gases influence how efficiently the planet retains heat. In the long run, the stopped Earth would not simply be a world with different sunlight. It would be a world whose atmosphere and biosphere were changing their composition together. Even geology would begin to look different under the new regime, not because the deep interior had changed, but because surface processes had. Rivers on the hot side might become more seasonal, driven by concentrated rainfall and evaporation. On the dark side, runoff could slow beneath expanding ice and frozen ground. Along the twilight belt, erosion might intensify, where persistent winds and shifting precipitation attacked unstable, already damaged terrain. Sediment would be moved in new directions. Deltas might starve or drown.
Canyons could begin forming in places that today are quiet plains, while other landscapes might fall strangely still beneath ice or drought. The stopped Earth would not only kill and spare, it would start sculpting a new face for itself. The light would be the next thing to become unnatural, after the roar of wind had begun to weaken in some places, after the first walls of water had spent part of their force, after dust, smoke, and spray had settled enough for the horizon to reappear. People would begin to notice that the sun was no longer behaving like the sun they had always known. It would still move, but it would move with a slowness so immense that it would feel almost fixed, as if the sky itself had been caught in thought. Morning would no longer be something that arrived, brightened, and passed into noon in a few ordinary hours. It would lengthen into something far stranger, a single chapter of light stretched across weeks and months.
This is the consequence of the new arrangement. If Earth stopped rotating on its axis but continued to orbit the Sun, day and night would not disappear. They would be transformed. The old 24-hour cycle would be gone, replaced by a solar day lasting roughly 1 year. The exact path of sunlight across the globe would still be shaped by Earth's orbit and its axial tilt, but the turning that once carried every region through regular alternations of light and darkness would no longer exist. Instead, one side of the planet would remain exposed to sunlight for an extremely long time, while the opposite side would remain in darkness just as long. Between them would lie a broad but shifting zone of low-angled light, neither properly day nor properly night, where the old boundaries of climate and habitability would begin to blur. That slow motion of the sun would be among the most psychologically disorienting changes on the planet. Human beings are not simply creatures who use daylight. We are creatures whose bodies are regulated by rhythm. The rising and setting of light influences sleep, hormones, appetite, mood, body temperature, and countless subtle internal cycles that evolved in company with the Earth's turning. Plants open and close with light. Birds time migration and song with light. Insects emerge with light. Predators and prey arrange their lives around light. To lose the normal sweep of the sky is not only to lose a clock, it is to lose one of the deepest regularities shared by nearly all life near the surface. Yet the thermal consequences would take time to unfold. That delay matters because it prevents the scenario from becoming a fairy tale of instant fire and instant ice. The atmosphere, and especially the oceans, hold immense amounts of heat. Continents also take time to warm and cool, though they do so more quickly than the sea. So, in the first days after the stop, the sunlit hemisphere would not immediately become an inferno, and the dark hemisphere would not immediately become a frozen tomb. Instead, the planet would enter a long transition. Existing warmth would linger. Winds would continue redistributing energy. Clouds would either reflect incoming sunlight or trap outgoing heat. Surface materials would respond according to their nature: desert rock, forest soil, wet marshland, open water, mountain snow, and city concrete would all absorb and release energy differently. That is one reason climate science is so useful here, even though a stopped Earth is not a real natural scenario. Researchers do understand the broad principles that govern how a planet gains, stores, and loses heat. We know sunlight is unevenly distributed over a sphere. We know darker surfaces absorb more solar energy than brighter surfaces.
We know oceans moderate temperature because water heats and cools slowly. We know air in motion carries warmth and moisture from one region to another. We know clouds can cool the surface below by reflecting sunlight and warm the surface beneath them by trapping infrared radiation. We know ice reflects a great deal of sunlight, creating feedbacks that can sustain cold conditions. And we know that once an atmospheric pattern is broken, new circulation systems emerge in response to the changed geometry of heating. On the long day side, the story would begin with persistence rather than violence. Morning light, once a passing event, would become an occupation. Shadows would creep so slowly that the movement of the sun would be almost imperceptible over a single human day. In some places, the light would continue to rise until it stood high and relentless over landscapes never meant to endure so much uninterrupted heating. Regions that had once cooled each evening would now remain under constant energy input. Soil moisture would begin to evaporate. Surface waters would warm.
Snowfields and mountain glaciers on the illuminated side would lose mass more quickly than under an ordinary day-night cycle. Cities, already damaged in many regions by the first atmospheric assault, would trap heat in broken concrete and exposed stone. Continents would generally respond faster than oceans. Land has less thermal inertia, so deserts, plateaus, plains, and urban surfaces under the prolonged sun would begin to heat strongly once cloud cover allowed enough radiation through. The exact pace would depend on latitude, cloudiness, wind, and local moisture. A humid region with thick, reflective cloud might remain far less extreme for a while than a clear, dry interior under direct sunlight, but the broad direction would be unmistakable. Evaporation would accelerate, surface water would shrink, plants would begin to experience prolonged stress, especially those adapted to a daily cycle of cooling and recovery. Crops would be among the first casualties, not always because they burned outright, but because their timing, water needs, and biology had been shaped by a world that no longer existed. Oceans on the illuminated side would resist temperature extremes better than land, at least at first. Water takes a great deal of energy to warm, and the upper layers of the sea are mixed by wind, currents, and turbulence. But resistance is not immunity. Under months of uninterrupted sunlight, especially if cloud patterns became less reflective and surface winds favored evaporation, sea surface temperatures would rise. Warmer water would mean more moisture entering the atmosphere. In some regions, that could feed thick cloud decks, perhaps softening the local heating below. In others, it could load the air with humidity and latent heat, fueling immense convection and intense storms of a new kind. The details are uncertain because the atmosphere would no longer be operating under familiar rotational constraints. But the possibility of a moist, overheated sunlit ocean driving powerful weather is well grounded in basic physics. There would also be strong regional contrasts on that bright hemisphere. High mountains would remain cooler than low plains. Coastal areas, influenced by surviving marine moderation, might remain less severe than continental interiors. Places with lingering snow or high albedo surfaces would reflect more sunlight and delay local warming. Areas beneath persistent clouds could be less brutal than clear skies just a few hundred kilometers away. But no region on the permanent day side would still behave like it once had. The old alternation between heating and cooling would be gone. Heat accumulated during long exposure would no longer be released each night in the usual way. The thermal memory of each place would begin to stretch day by day,
into a new pattern. If the day side would change slowly into something increasingly hostile, the dark side would transform with a different kind of patience. There would be no instant plunge to absolute cold. Air and ocean currents would carry residual warmth for a time. Ground that had seen recent sunlight would continue radiating stored heat. Urban materials would cool gradually. Coastal waters, especially large oceans, would release warmth accumulated over previous seasons. But once sunlight stopped arriving, every place on the night side would begin a long accounting with the sky. Without incoming solar energy, heat would continue leaving the surface as infrared radiation. Clouds, where they existed, could slow that loss, but not stop it. Over days and weeks, temperatures would fall. The rate of that fall would vary enormously. Dry continental interiors generally cool quickly because they lack the thermal buffering of the sea. Oceans cool more slowly. Ice and snow, if they formed, would alter the balance further by reflecting any faint returning light and insulating the ground beneath in complicated ways. Still, the direction would remain clear.
Extended darkness would allow the dark hemisphere to cool beyond anything most modern climates experience outside the highest latitudes or unusual winter conditions. As the cooling deepened, atmospheric moisture would begin to condense and freeze more readily. Snow cover would expand where enough moisture remained. Frost would push into regions that had never known it. Tropical landscapes in prolonged darkness would become alien to themselves. One of the most profound consequences of the long night would be biological before it was human. Photosynthesis near the surface depends on light. Remove light for months, and the primary productivity of ecosystems collapses. On land, green plants would consume stored energy and then fail if darkness persisted too long. Some species could endure dormancy, some seeds could wait, some roots and bulbs could survive for a season. Mosses, lichens, fungi, and microorganisms might persist in pockets, but forests, grasslands, crops, marsh plants, and planktonic communities at the surface would all be under immense pressure. The crisis would ripple upward through every food web. Herbivores would lose forage, pollinators would lose flowers, predators would lose prey. On the dark side, cold would be one destroyer, the absence of light would be another. The oceans of the night side would be especially complex. Open water, even under darkness, stores enormous heat compared with land. For a while, the sea would act as a reservoir, softening the cooling of adjacent coasts. But the surface would steadily lose heat to the atmosphere and space. Sea ice would begin forming in colder regions and then spreading where conditions allowed. That process would not merely place a frozen lid over the water. It would affect salinity, circulation, albedo, and exchanges of heat and moisture between ocean and air. In today's world, sea ice already plays a central role in polar climate. On the long night side of a stopped Earth, sea ice could advance far beyond its modern limits, reshaping marine ecosystems and atmospheric patterns alike. It is tempting to imagine the dark side as empty, but that would be too simple. There would still be light of other kinds. Moonlight when the moon was present, starlight, auroral displays in certain regions, volcanic glow where the planet's interior pierced the surface, human fires and artificial illumination where any civilization remained capable of making them. More importantly, there would still be motion and weather. Darkness does not mean stillness. As the illuminated hemisphere warmed and the dark hemisphere cooled, pressure differences would grow.
Air would begin to organize itself around those contrasts, seeking to move heat from where it was abundant to where it was lacking. In that sense, the night side would not merely freeze in silence, it would become one half of a planetary engine. Between the scorching promise of the day side and the deepening cold of the night side, a new zone would begin to attract both scientific interest and human hope. This would be the region near the moving boundary between light and darkness, where the sun remained low, or where twilight lingered for very long spans. It would not be a sharp line drawn cleanly around the globe. Clouds, mountains, atmospheric scattering, and latitude would blur it, but conceptually it matters, because here the energy balance might remain closer to tolerable for longer than in either extreme. The air would still be unstable, winds could be fierce, weather would likely be strange, yet this twilight belt could become the most promising corridor for liquid water, moderate surface temperatures, and persistent human survival. The idea is not imaginary in spirit, even if the scenario is. Planetary scientists discussing tidally locked exoplanets often ask similar questions. On a world that always shows the same face to its star,
could a habitable zone exist between the burned day side and the frozen night side? The answer depends on atmosphere, ocean circulation, cloud behavior, and composition, but the concept itself is serious. Earth would not truly become a tidally locked exoplanet in this scenario because its orbital and axial conditions are different. Still, the analogy is useful. It reminds us that habitability is not always a simple matter of whole planets being either good or bad for life. Sometimes it is a question of belts, margins, and boundaries. The twilight belt, however, would not be gentle by default. In many places, it could become the windiest region on Earth. Warm air from the day side would try to flow toward cooler regions. Cold, dense air from the night side would try to sink and spread. Pressure gradients could sustain powerful, persistent winds along or across the zone of contrast. Cloud bands might gather there. Condensation could be strong where humid, warm air met colder layers. Some stretches might be rainy, even stormy. Others could be dry if descending air dominated. Mountains within the twilight belt could create dramatic local differences, making one valley marginally habitable, while another nearby remained barren, frozen, or wind-scoured. Even the color of the world would change there. On the day side, the light might be hard and bleaching, flattening details beneath a sun that refused to leave. On the night side, the world would withdraw into blacks, silvers, blues, and the muted glow of whatever remained. But in the boundary zone, the atmosphere itself might paint long, complicated gradations. Dust and aerosols from damaged continents could redden the low sun. Thick cloud could reflect pink, gold, and copper. Long horizons of oblique light could make mountains seem suspended and seas appear metallic. It is one of the ironies of catastrophe that some of its most visually beautiful effects arise from conditions deadly to ordinary life. As the weeks passed, the new circulation of the atmosphere would become the true architect of climate. Earth's present winds are strongly influenced by rotation through the Coriolis effect, which bends moving air and helps organize trade winds, westerlies, storm tracks, and large rotating weather systems. Remove Earth's spin, and that organizing influence vanishes. Air would still rise where strongly heated and sink where strongly cooled, but its movement would no longer be deflected in the same way. Instead of familiar belts of east-west flow,
The atmosphere would tend more toward direct transport between hot and cold regions. In simple terms, air would try to travel from the day side toward the night side near the surface, while return flow aloft could move in the opposite direction, though the real pattern would be modified by terrain, moisture, and the evolving distribution of heat. This would create a planetary circulation unlike the one humanity evolved under. A broad rising zone could develop over the warmest illuminated regions, where intense heating made air buoyant. That air, rich in moisture where oceans remained, would rise and spread aloft. Somewhere downwind toward the darker hemisphere, it would cool, lose energy, and sink. Near the surface, colder, denser air could then flow back toward warmer regions, completing immense loops. These loops would not be neat or perfectly symmetrical. Continents break the planet's surface into roughness, mountain ranges force air upward, oceans release heat unevenly, cloud formations change the energy balance. Yet the broad theme would remain. The atmosphere would become a machine for exporting heat from eternal day to endless night. In some ways, that transport would be a gift. Without it, the day side might become even hotter and the night side even colder. Atmospheric circulation is a bridge, but it would be a difficult bridge to live beneath. Strong pressure contrasts could sustain powerful, persistent winds for long periods.
Regions along the transfer routes might endure constant air movement, shifting cloud decks, and highly variable precipitation. Calm weather, in the familiar sense, could become rare in some latitudes. A new definition of normal would emerge, and it might be one in which stillness itself was unusual. Clouds deserve special attention because they could become one of the great moderators of the stopped world. On the bright hemisphere, extensive cloud cover would reflect incoming sunlight and reduce surface heating below. Tropical Earth today offers examples of this kind of regulation. Warm, moist surfaces promote cloud formation, and those clouds can limit further heating. On the other hand, clouds also trap outgoing heat, especially at night or over cooler surfaces. On the dark side, cloud cover might therefore reduce the severity of radiative cooling in certain regions, acting like a blanket over a cooling world. The exact result would depend on cloud type, altitude, thickness, and distribution. That uncertainty does not weaken the scenario, it enriches it. It tells us that the future of a stopped Earth would not be governed by heat and light alone, but by the atmosphere's intricate response to both. Precipitation would also be reorganized. In today's climate, rain belts are tied to moving patterns of convection, seasonal migration, ocean temperatures, and the deflecting influence of rotation. On the stopped Earth, some zones might receive extraordinary rainfall, where moist, warm air rose and cooled. Others might become desiccated under descending air that suppressed cloud formation. River systems on the day side could briefly swell with meltwater and intense rain, before later shrinking as evaporation and ecological collapse advanced. On the night side, precipitation might increasingly fall as snow or ice particles as temperatures declined. In the twilight belt, rain, sleet, freezing rain, and fog could all occur depending on local conditions. The hydrological cycle would remain alive, but it would no longer resemble the one mapped by modern climatology. Ocean circulation would enter its own period of reinvention. Today, the great currents of the world ocean are shaped by winds, differences in water density, basin geometry, and Earth's rotation. The Gulf Stream, the Antarctic circumpolar current, and the broad gyres of subtropical oceans all depend in important ways on a rotating planet. Without rotation, the sea could no longer organize itself into the same familiar spirals and boundary currents.
winds would change. Temperature contrasts between hemispheres of light and dark would intensify. Surface salinity patterns would shift as evaporation, rainfall, and ice formation were redistributed. Over time, the ocean would begin to carry heat not according to the old map of gyres and overturning, but according to the new imperative of connecting a hot side and a cold side. This would not happen overnight. The ocean is slower than air. Its immense mass and depth give it memory. Surface waters would respond first, especially where winds and heating were strongest. Deep circulation would adjust over longer spans as density gradients changed. If the day side experienced strong evaporation, surface waters there could become saltier in some regions, altering their density and mixing behavior. On the night side, freezing sea ice would reject salt into the surrounding water, making nearby unfrozen water denser and potentially driving sinking motions. In the boundary regions, the meeting of warm and cold waters could generate powerful fronts, fog, and biologically productive zones if enough life remained to use the nutrients stirred upward. That last qualification is important. Physical habitability is not the same as ecological continuity. A place with liquid water and moderate temperature may still be poor in life if the systems that once fed it have failed.
The first great biological collapse would therefore not be only a matter of death from heat or cold. It would be a matter of broken timing. Plants on the day side would receive too much uninterrupted light, and in many regions, too much heat and evaporative stress. Plants on the night side would receive no light at all. Marine plankton near the surface on the day side might bloom at first in some waters if nutrients were available, but would also face overheating, stratification, or shifting chemistry. On the dark side, photosynthetic plankton would disappear near the surface once light was gone long enough. Since plankton form the base of many marine food webs, their collapse would ripple upward into fish, seabirds, and larger predators. Forests would illustrate the complexity beautifully and tragically. On the day side, some forests might remain green for a while, especially where cloud, moisture, and altitude moderated conditions. But forests are not merely collections of trees. They are climates in miniature, dependent on soil moisture, fungal networks, insects, pollinators, and regular cycles of evaporation and cooling. Prolonged heat and disrupted rainfall could turn living canopies into stressed, thinning systems vulnerable to fire, pests, and mortality. On the night side, forests would confront cold and darkness. Evergreen species can endure winter because winter ends. Deciduous trees enter dormancy because spring follows. But months of extended night beyond any evolved expectation would push many plant systems beyond their normal resilience. Forests would not vanish everywhere at once. They would begin to fail unevenly, region by region, according to how far the new sky exceeded the old tolerances. Grasslands, wetlands, and agricultural systems would suffer differently. Grasses often recover well from seasonal stress, but not from climate regimes that erase the seasonal logic they evolved with. Wetlands depend on water levels, sunlight, and temperature-sensitive microbial processes. In darkness, many would stagnate or freeze. Under endless light and rising heat, others would shrink and dry. Agriculture would be especially fragile because it is not merely ecological, it is synchronized. Sowing, flowering, fruiting, harvesting, storage, and transport all assume predictable time. A world in which the sun no longer rises and sets each day is a world in which the agricultural calendar loses its foundation. For human societies trying to persist,
This would be devastating. Even if some communities reached the twilight belt, their survival would depend on more than temperature. They would need crops capable of growing under unusual light regimes or controlled cultivation systems independent of the natural sky. They would need stable water supplies, not poisoned by salinity shifts, sediment, or contamination from the first global destruction. They would need some source of energy and shelter from persistent winds. The physical plausibility of the twilight belt as a refuge does not make it comfortable. It makes it less immediately fatal than the extremes. That is a very different thing. There would be feedbacks everywhere. If vegetation died back on the day side, bare ground could reflect more or less sunlight depending on what remained, altering local heating. Dust from dried landscapes could rise and either cool the surface by reflecting light or warm the atmosphere by absorbing it. If extensive snow and ice expanded on the night side, their high reflectivity would matter once sunlight eventually returned in the long annual cycle, delaying warming and perhaps maintaining cold conditions longer than expected. Ocean ice would alter not only albedo, but gas exchange and ecosystem structure. Every part of the Earth system would be interacting with every other part, often in ways that amplify change rather than soften it. This is why the stopped Earth becomes so fascinating as a thought experiment.
It begins with a single, impossible act, and then unfolds through entirely real relationships: energy budget, fluid motion, heat storage, reflection, convection, biological dependence on light, geography. These are the threads. Once they are pulled, the tapestry changes without requiring new magical rules. The most uncertain details are local, not fundamental. We may not know exactly where the cloudiest refuge would lie, or how quickly one coastline versus another would freeze or bake, but we know enough to say that the planet would separate into thermal worlds, and that life would be forced toward the margins between them. Time would also begin to feel different. A person on the day side could no longer trust evening to arrive in the familiar sense. A person on the night side could no longer trust dawn. Communities would have to invent artificial schedules simply to preserve sleep, labor, and social coordination. But outside those human arrangements, the planet would be obeying a different, slower rhythm. The sun's position would change so gradually that entire phases of climate might unfold beneath nearly the same quality of light. A city in perpetual dawn-like conditions could endure weeks of stress before sliding into something hotter. A coast under long darkness could become colder day by day, even while the stars looked unchanged. Human attention, evolved for daily cycles, would struggle to feel the movement of such a year-long day. And yet, the movement would continue. Earth would still orbit the sun. The line dividing light and dark would not remain fixed forever over exactly the same lands. Over the course of the orbital year, illumination would migrate. Regions roasting under long exposure would eventually move toward lower sun angles. Regions trapped in darkness would eventually approach the return of light. The twilight belt would shift as well. This adds another layer of difficulty. Habitability would not be entirely stationary. A region that served as refuge for months might later drift toward more severe heating or colder darkness, depending on season, latitude, and the geometry of the axis. Survivors would need not only places to live, but a new understanding of planetary time vast enough to anticipate migrating danger. The axial tilt would remain important here. Earth's seasons today arise because the axis is tilted relative to its orbital plane.
On a rotating planet, that tilt changes the height and duration of the sun across the year. On a non-rotating Earth, the tilt would still matter, but expressed through a much slower unfolding of light over the annual cycle. Some latitudes would receive especially long periods of oblique light. Others could experience more direct solar exposure when their hemisphere leaned toward the sun. The resulting patterns would be difficult to intuit because human experience offers no close parallel. Yet the tilt would ensure that the stopped world was not split forever into one permanent hot face and one permanent cold face in a perfectly simple way. Instead, the geometry of light would evolve across the year, dragging climate zones with it. The biosphere, already damaged, would face this moving challenge with little flexibility. Migration is one possible answer, but migration requires corridors, food, and a pace compatible with the speed of environmental change. Trees cannot walk, coral reefs cannot migrate over land, soil communities are local. Even mobile animals are constrained by terrain, breeding cycles, competition, and the collapse of the habitats linking one survivable place to another. Some birds and large mammals might follow the shifting twilight if pathways remained. Many more species would fail before they could adapt. Evolution can work wonders over deep time. It is not a rescue service for sudden planetary reorganization. The oceans might preserve life longer than land in some respects.
Marine systems include deep environments independent of sunlight at the surface, relying instead on falling organic matter or chemical energy from hydrothermal vents and cold seeps. Deep-sea organisms would not be physically untouched by the global changes because temperature, circulation, and food supply from above would all be altered eventually. But they would not lose sunlight because they did not depend on it in the first place. In that sense, the deep ocean could become one of the great reservoirs of biological continuity, even as the sunlit surface biosphere convulsed. Microbial life, as always, would be especially resilient. It is one of the humbling truths of Earth history that worlds lethal to large, familiar organisms may still teem with small, stubborn life. If one listened from far enough away, the planet would still sound alive. Winds would move, water would shift, clouds would form and thin, ice would grow and fracture. Yet much of the life visible to human eyes would be under severe stress. The first great biological collapse would not necessarily look dramatic everywhere. In some places, it would appear as absence. No insects at dusk, because dusk no longer comes. No bird chorus, because the trees no longer flower. No fish in a coastal shallows clouded with sediment and altered currents. No amphibians singing from wetlands that have dried on the bright side or frozen on the dark side. Catastrophe is often imagined as noise. Sometimes it is a silence arriving species by species. Human cultures that survived the opening destruction would begin to notice another truth as well. The old distinction between weather and climate would blur in ordinary speech. On the rotating Earth, weather is the day-to-day experience of the atmosphere, while climate is the larger pattern. On the stopped Earth, daily change would diminish in some places because the sun itself would change so slowly. Instead of tomorrow's forecast feeling meaningfully different from today's, whole regions might endure long atmospheric moods, a prolonged heat, a long dark freeze, a seasonless gale, a belt of recurring cloud and rain. The sky would become less like a rotating theater of scenes and more like a slowly shifting architecture. By now, months into the new regime, the first emergency of motion
would have given way to the emergency of imbalance.
The old Earth was dynamic, but balanced within familiar limits. The stopped Earth would also be dynamic, but organized around sharper contrasts and much longer exposure. Energy would accumulate where it should not linger, and vanish where it should not vanish. The atmosphere and ocean would labor constantly to soften that contrast, yet in softening it, they would create the very winds, currents, cloud systems, and boundary storms that made the new world difficult to inhabit. This is why the search for survivable ground would narrow toward very particular places, not simply cool places, not simply bright places, not simply coasts or mountains or plains. Survivable ground would likely mean places where several conditions overlapped for a time: tolerable light, manageable temperature, access to fresh water, some shelter from persistent winds, and perhaps soils or marine zones still capable of supporting life. Such places might appear in arcs along the twilight belt, in highland regions with moderated conditions, on certain coasts with oceanic buffering, or in valleys that happened to soften the new atmospheric regime. The geography of refuge would be subtle. It would reward not human ambition, but patient observation of a changed planet. And still, even these refuges would be temporary in many cases, because the line of light and darkness would continue its slow annual migration. A settlement established under long twilight might, months later, face a brighter and hotter sun. Another might slide into longer cold and weaker light. The idea of permanence would weaken. Mobility, storage, and foresight would become as important as fortification. Earth would no longer be a world of ordinary seasons. It would be a world of migrating extremes, separated by unstable margins. The next part of the story belongs to life and to us. Once the atmosphere has found its broad, new roots, once the oceans have begun to abandon their familiar currents, once the first wave of biological loss has made clear how dependent the living surface was on daily light and darkness, the question changes. It is no longer only how the planet reorganizes itself. It becomes which forms of life can endure inside that reorganization, and where human beings, fragile and adaptable at the same time, might try to make a future in the narrow country between fire and ice. The first communities that endured would learn to read the planet in a new way, not by borders, not by old nations, not by the roads and shipping lanes that had once bound distant places together, but by gradients of light, water, wind, and shelter. Maps drawn before the stop would still show mountains, rivers, and coastlines, yet their meaning would have changed. A fertile delta on the old Earth could now be drowned, salted, or caught between surging seas and unstable weather. A remote plateau, once little more than a cold margin of the habitable world, might become one of the few places where air, temperature, and terrain allowed a difficult kind of continuity. Survival would no longer begin with ownership. It would begin with interpretation. That interpretation would be slow, local, and often expensive. People would need to discover which valleys held moisture without becoming storm traps, which coasts still offered fish without lethal surges, which uplands softened the heat of the bright side without sliding too deeply into darkness, and which stretches of the twilight belt had enough stability to support long-term settlement. It would not be enough to flee from fire toward cold, or from cold toward light. The stopped Earth had destroyed the usefulness of simple opposites. A place could be cool but dry, bright but barren, temperate but wind-scourged, wet but salted, sheltered but isolated from any broader food source. The world would not offer one obvious refuge. It would offer a scattered geometry of partial mercies. Among the first lessons would be a renewed respect for water in all its forms. On the old Earth, fresh water often seemed abundant wherever rivers ran, glaciers fed reservoirs, or rain returned in expected seasons. On the stopped Earth, each of those assumptions would fray. Some rivers would weaken as old rainfall patterns dissolved. Others would become violent and unreliable, fed by sudden melt or by concentrated storms. Ice, on the dark side, might store immense quantities of fresh water, while placing them beyond practical reach. Coastal aquifers could be spoiled by salt intrusion. Reservoirs built for old climates would fill with sediment, dry under prolonged heat, or become inaccessible after infrastructural collapse. Communities that survived would therefore be drawn not only to moderate light and temperature, but to stable hydrology, to springs, sheltered catchments, high lakes, groundwater basins, and coastlines where desalination or careful harvesting might still be possible. Food would demand an even more radical rethinking. Agriculture on the spinning Earth was never simply the act of growing plants in soil. It was an agreement with seasonality, an art built upon predictable warmth, cold, rainfall, daylight length, pollinators, and the long inheritance of domesticated species tuned to those rhythms. Once the daily cycle and ordinary seasons disappeared, many familiar crops would fail, not because they lacked basic nutrients, but because the timing of their lives had been broken. Some plants could endure long light, but not relentless heat. Others could tolerate cool conditions, but not the prolonged absence of darkness or the altered chemistry of the soil. Pollinators might vanish from a region before the plants that needed them. Wind-borne pollen could fail if flowering no longer synchronized within a community of plants. Seeds saved from the old world might become relics of a climate that no longer existed. The first successful cultivation on the new Earth would likely look less like open field farming and more like managed ecology. Shade structures, wind barriers, terraced moisture traps, underground storage, enclosed growing spaces, and carefully controlled cycles of artificial darkness could become as important as soil itself. Human beings have grown food in difficult places before, on mountain slopes, in deserts, in river deltas, in cold northern light, and under glass in polar stations. The stopped Earth would not erase that ingenuity. It would make it universal. A greenhouse would no longer be a specialized tool. It might become the model for civilization, a deliberate pocket of rhythm built inside a world that no longer offered rhythm freely. This would be especially true in the twilight regions, which might appear promising from a distance, but would remain unstable in practice. Light there would often be low and oblique. That could be helpful for temperature, yet insufficient for many crops unless enhanced by reflective surfaces, carefully chosen plant varieties, or artificial supplementation. Winds could strip moisture from leaves and scour topsoil. Clouds might linger for weeks. Rain could come in irregular pulses rather than in familiar seasonal patterns. There would be places where edible plants could still be cultivated outdoors, especially if local terrain moderated the climate, but broad-acre abundance would be rare. The stopped Earth would favor intensity over spread, careful management over easy fertility. Animal husbandry would face its own difficulties. Grazing animals require vegetation, water, and protection from temperature extremes. Predators, disease, breeding cycles, and migration patterns all depend upon ecological stability. In a world where grasslands shifted, insects vanished, and the daylight regime no longer matched inherited behavior, many domesticated herds would shrink sharply or disappear. Smaller, more controlled livestock might fare better than large herds. Species that tolerate confinement, altered light, and diverse feed could become more important. Aquaculture, too, might move inland or into sheltered marine pockets, though the instability of water chemistry and temperature would make it difficult in many places. In all of this, humanity would discover again that food is not manufactured wealth. It is a living negotiation with energy, water, and time. Time itself would have to be invented anew. On the old Earth, clocks are social instruments, but they harmonize with something older than society: sunrise, noon, evening, night. The body expects those markers even when it pretends to ignore them. On the stopped Earth, such markers would become unreliable over human timescales. A community under prolonged twilight might see only subtle changes in solar angle over many days. A settlement on the bright side might live beneath a long, climbing sun that never truly set. In darkness, people could maintain lamps and schedules, yet the sky would offer no dawn to confirm the effort. This would matter more deeply than it first appears. Without external rhythm, internal rhythm phrase, sleep disorders, mood disorders, errors of judgment, and social fatigue would become quiet hazards of the new world, even in places where food and water remained available. The civilizations that endured longest would therefore be the ones that treated time as infrastructure. They would create regular cycles of work, rest, shared meals, artificial evening, artificial morning, perhaps even communal seasons, marked by chosen ritual rather than by weather alone. Architecture would support these rhythms. Buildings might be designed with layered light control, thick insulation, and acoustic quiet, allowing interiors to simulate night even under an endless sun, or to preserve wakefulness through carefully timed illumination under months of darkness. Public life would become partly astronomical and partly biological. The sky would still matter, but not as master. Human communities would need to become their own clockmakers. Energy would be another dividing line between persistence and decline. Regions under prolonged sunlight might seem rich in power at first glance. Solar energy would indeed be abundant there, provided systems could survive heat, dust, and weather. Yet, constant brightness does not eliminate other needs. Cooling, water pumping, food cultivation, and shelter maintenance would all demand reliable infrastructure. On the night side, solar generation would fail for long stretches, and stored energy would become critical. Wind could be powerful in some zones, but turbines are vulnerable to extreme conditions and require maintenance. Hydropower would depend on watersheds altered by the new climate. Fossil fuels, where still accessible, could provide temporary stability, but not indefinitely, especially if extraction and transport systems had collapsed with the old world. The energy map of the stopped Earth would be fragmented, and with it, the map of complex civilization. Trade would survive only in altered form. The old global economy relied on predictable seas, ports, aviation corridors, roads, satellites, synchronized markets, and a trust that another sunrise would arrive before the food spoiled. Much of that world would be gone. Long-distance exchange might continue along narrow, carefully maintained routes within the most stable belts,
especially if ships or overland caravans could move between surviving communities.
But the age of seamless abundance would end. Self-sufficiency would become more valuable, not because isolation is ideal, but because dependence on remote systems would be too dangerous. The communities that lasted would likely be those that combined local resilience with selective networks of exchange, trading seeds, knowledge, medicine, and tools, rather than living on the assumption that everything can come from somewhere else. Medicine, too, would return to fundamentals, while still needing science desperately. The first wave of deaths after the stop would not be the end of the crisis. Injury, infection, malnutrition, chronic stress, exposure, contaminated water, and disrupted sleep would all become major threats. Cold, dark regions would face hypothermia and vitamin deficiencies. Hot, bright regions would struggle with dehydration, heat illness, smoke inhalation, and compromised sanitation. Twilight settlements might fare better climatically, while still suffering from scarcity and the persistence of new pathogens in altered ecosystems. The stopped Earth would not erase modern medical knowledge, but it would challenge the systems that make that knowledge actionable. Refrigeration, sterile supply chains, surgical lighting, pharmaceuticals, and coordinated care all depend on a functioning technological web. Surviving societies would need to rebuild medicine as both a local craft and a precious science. Some places would emerge as natural laboratories of adaptation, a wind-sheltered inland basin at mid-latitude, lying within long twilight for much of the year and fed by stable mountain water, could become a rare center of population. A rugged subpolar archipelago with fisheries, geothermal heat, and limited but manageable climate extremes might serve as another. High volcanic regions near the old tropics, cooled by altitude, yet close enough to moving margins of light to avoid the worst darkness, might briefly support clustered settlements if water remained. None of these places would be easy, but ease would no longer be the measure. The new measure would be whether a landscape offered enough of the old Earth's gifts in a narrower, harsher package. As generations passed, human culture itself would begin to bend around geography and sky in ways difficult to imagine from within the old world. Languages would absorb new distinctions for light, for transitional weather, for the shifting edge of habitability. Children born under a sun that lingered for months would not inherit the same instincts about morning and evening as their ancestors. Stories, rituals, and calendars would emerge from the movement of the twilight belt, from the return of usable light to a settlement, from the long, cold descent into dark, from the reopening of a river route, from the flowering of a greenhouse valley, from the safe migration of fish into a coastal inlet. Human beings always build meaning from the patterns that govern survival. The stopped Earth would offer very different patterns. That cultural adaptation would not mean the crisis had ended. Much would still depend on the slow, physical reshaping of the planet itself. Even after the immediate atmospheric violence and the first climatic reorganization, the Earth would continue adjusting to the loss of rotation. One of the deepest long-term consequences would be the redistribution of water. The modern equatorial bulge, maintained by rotation, allows the oceans to stand slightly farther from the center of the planet at low latitudes than they do at the poles. Remove the rotational effect that helped maintain that bulge, and over time, water would migrate toward the poles. This would not happen as a sudden avalanche of ocean from equator to pole,
but as a long geophysical settling, a reallocation of the sea according to a new gravitational balance. The implications are difficult to overstate. Equatorial and low-latitude regions,
already damaged heavily by the initial catastrophe and by prolonged heating, could eventually lose significant ocean cover in some areas. Former seafloor might emerge. Some coastlines would retreat. Other basins at higher latitudes could deepen beneath accumulating water. The planet's map would not merely shift around the margins. It could be remade. Where today there are warm, shallow seas, there might one day be exposed sediment plains, saline basins, or strange interior depressions. Where today polar coasts and subpolar seas limit settlement, future ocean expansion could redraw entire continental outlines. The stopped Earth would be a planet not only climatically unfamiliar, but cartographically transformed. Because this process would unfold slowly, perhaps over very long spans compared with human crisis planning, it would not dominate the first centuries as strongly as weather, water access, and food. But it would matter to any civilization that survived long enough to think in geological rather than seasonal time. Ports could become useless not only because of storm damage, but because the sea itself was departing. New navigation routes could open across high-latitude waters that once bordered ice or land. Sedimentary plains, rich in the remnants of former oceans, could appear in low-latitude belts where the sun remained dangerous, but where future twilight migration might briefly create windows of access. Human history on the stopped Earth, if it endured, would unfold against a coastline that refused to stay still. Erosion and sedimentation would join that transformation. River systems adjusted to old rainfall and sea level would be forced into new behaviors. Some rivers might incise deeply as base levels shifted. Others could spread into braided networks across newly emerging flats. Wind would redistribute fine sediments across vast distances, especially where vegetation had died back. Dust-less deposits could accumulate in some twilight interiors, creating fertile but unstable soils. In cold regions, advancing ice and permafrost would grind and fracture rock, storing sediment for later release if light returned and thaw resumed. Landscapes that once took millions of years to evolve could be hurried into new trajectories by the combined force of altered climate and migrating water. There is a temptation to ask whether the deep Earth, the molten interior and moving plates below the crust, would care about the lost rotation. The short answer is that the mantle and core have their own immense inertia and timescales. Plate tectonics would not simply stop, nor would volcanism vanish because the surface day had become a year long. Mountains would still rise and erode, earthquakes would still occur, volcanoes would still open paths from the interior to the sky. Yet the meaning of those processes would change when set against a transformed surface. A volcanic region on the dark side might provide heat, chemical energy, and meltwater, becoming a biological refuge. Geothermal zones could support human settlements where ordinary climate had become too severe. The stopped Earth would not only take away. In scattered places, the deep planet might offer substitute sources of warmth and continuity. Life would gather around such substitutes. Even on the old Earth, life shows a remarkable tendency to exploit margins and refuges. It flourishes in hot springs, under Antarctic ice, around hydrothermal vents, inside porous rocks, and within desert crusts so dry that from a distance they appear sterile. The stopped Earth
would magnify the importance of those capacities. Microbial communities would likely become the enduring foundation of many ecosystems, especially where sunlight failed or ordinary plant productivity collapsed. Chemosynthetic life in the deep ocean, already independent of the sun, could continue with less disruption than the surface biosphere.
Fungi and bacteria would mediate the decomposition of the old living world and the birth of new nutrient cycles. Lichens and hardy pioneer species might creep across the margins of newly exposed land or freshly stabilized sediments. Over longer spans, evolution could begin answering the stopped Earth in its own patient language. This is the point where caution matters. Evolution does not guarantee complexity, beauty, or resilience on human timescales. It responds to differential survival and reproduction. On a world defined by extreme gradients of light and darkness, wind-stressed margins, shifting coastlines, and engineered human refuges, lineages that tolerated irregular light cycles, low productivity, broad thermal ranges, and opportunistic feeding might have the best chance to diversify. Generalists often outlast specialists during crisis. Small organisms often outlast large ones. Aquatic and subterranean refuges often preserve continuity better than exposed, richly layered terrestrial ecosystems. If the stopped Earth ever developed a mature biosphere under its new regime, that biosphere might look less luxuriant than the old one, more concentrated around margins, caves, coasts, estuaries, and engineered oases. Human beings would confront a different evolutionary pressure, one filtered through culture. Biological evolution in our species is too slow to provide quick rescue from planetary transformation, but cultural evolution can move fast. Shelter design, agriculture, social organization, medicine, timekeeping, migration strategy, and energy use can all change within generations. In that sense, humanity's greatest adaptive trait would not be strength, speed, or tolerance of heat or cold. It would be the ability to construct pockets of order, shared memory, and deliberate rhythm inside a world that no longer offered them naturally. This is not a sentimental claim. It is a practical one. People survive not merely by enduring environments, but by redesigning the relationship between body and environment. Still, there would be hard limits. A species that evolved on a rotating world under a predictable day-night cycle cannot escape physics by intelligence alone. Some regions of the stopped Earth would remain beyond reasonable habitation, no matter how clever a society became. The hottest parts of the long day side might be too dry, too bright, or too thermally punishing for sustained settlement without extravagant energy inputs. The deepest dark and cold of the night side could demand more heat and stored resources than many communities could provide. The moving margins of habitability would expose settlements to long-term uncertainty. Human survival would, therefore, likely remain partial. Not everywhere, not billions, at least not easily. Pockets, corridors, clusters, networks. Civilization would become archipelagic in spirit, even where it occupied continuous land. This leads to the quiet central question the stopped Earth asks about us. Could we survive? Not in the dramatic sense of a handful of heroes enduring one storm, but in the sober sense of whether a complex, thinking species could preserve continuity through a planetary loss of rhythm. The answer is not a clean yes or no. On one hand, the initial catastrophe and subsequent climatic reorganization would be devastating beyond any natural disaster in human history. Enormous populations would be lost, ecosystems would collapse, infrastructure would fail.
vast parts of the globe would become temporarily or permanently hostile. On the other hand, the Earth would still have gravity, atmosphere, water, internal heat, chemistry, and regions of intermediate climate. That matters. We would not be surviving on a shattered moon or a sterile rock. We would be surviving on a wounded Earth that still retained many of the ingredients of habitability. That distinction is profound. It means the stopped Earth,
for all its violence, is not a total negation of life. It is a rearrangement of possibility. The old, generous distribution of ordinary habitats would be gone, replaced by narrow, conditional, and shifting zones. Many species, including perhaps many human societies, would fail in the transition. But some life would persist because the planet would still be chemically fertile and physically active. Even a world with 1 day per year is still a world with oceans, clouds, mountains, and exchange between surface and sky. The lesson is not that life is invincible. It is that life and habitability are often matters of degree, geometry, and adaptation rather than absolute categories. Seen from far enough away, the stopped Earth would remain beautiful. This is another difficult truth. Beauty does not guarantee mercy. A crescent boundary of long sunset could glow with colors no ordinary evening has ever sustained. A dark hemisphere veined with auroras and ice could look serene from orbit. Vast cloud shields over the hot side could shimmer like polished silver. The oceans, redistributed over new shapes of coast, would still reflect the sun. Mountains would still cast long shadows. The planet would still turn around the sun, though not around itself, and that motion alone would keep the line between fire and frost slowly migrating across continents and seas. One could imagine a photographer in orbit making images of overwhelming calm, while below, life struggled along the margins. That tension between beauty and indifference has always existed. Our world feels stable because it is familiar, not because the cosmos has promised to keep it so. The stopped Earth reveals how much of our idea of normal rests on hidden motion. We walk on a planet spinning through darkness, orbiting a star tilted just enough to produce seasons, massive enough to hold air, warm enough to keep water liquid, active enough to renew landscapes, yet gentle enough, most days, to let trees rise and birds rest and people sleep. None of those conditions is guaranteed by moral necessity. They simply happen to coincide here, now, within the long story of Earth. This is why speculative questions can be scientifically valuable, even when their premise is impossible. They do not predict the future. They expose the structure of the present. By imagining a world in which rotation stops, we learn what rotation quietly does for us. It organizes day and night. It shapes winds and ocean currents. It contributes to the distribution of heat, water, and even sea level. It helps set the tempo of weather, the logic of ecosystems, and the biological clocks within bodies. Much of ordinary life depends not on grand, dramatic forces, but on continuous, unnoticed regularity. The old Earth was generous, in part because it repeated itself every day. There is something humbling in that. Human civilization often tells its story through invention, law, war, language, trade, and memory. Those things matter, yet beneath all of them lies a quieter foundation. Morning, evening, tides, seasons, rainfall that broadly returns when expected, winds that, while dangerous at times, belong to an intelligible pattern, oceans whose currents stabilize rather than betray whole climates,
a horizon that brightens and darkens on time. Without those background fidelities, history itself changes character. It becomes less a narrative of ambition and more a negotiation with recurrence and refuge. Perhaps that is why the imagined survivors of the stopped Earth feel so compelling. They would not simply be enduring a harsher planet. They would be rebuilding a sense of order under a sky that no longer gave it freely. Their clocks would be acts of resistance against celestial irregularity. Their farms would be arguments with light. Their settlements would be carefully placed compromises between heat, cold, water, wind, and time.
Their songs and stories would likely remember the old 24-hour day, the way some cultures remember lost rivers, lost coasts, or vanished migrations, not as abstract data, but as a pattern that once made life easier to carry, and the rest of life, where it endured, would carry on with its own quiet solutions. Microbes under stone, fish in twilight currents, algae blooming in brief windows of usable light, moss taking hold on cold, damp rock, insects returning where sheltered greenhouses leaked warmth into still air, birds, perhaps, learning new routes along the migrating edge of habitable land. Human beings often imagine survival as a loud victory. The biosphere usually practices it as patience. Patience is, in a way, the final scale of the stopped Earth. The first minutes belong to violence. The first months belong to imbalance. The following years and centuries belong to adaptation, settlement, erosion, migration, and the slow instruction of new climates. The millennia beyond that belong to deeper transformations still. Coastlines moving, waters redistributing, ecosystems reassembling, perhaps even civilizations becoming native to the long day and long night in ways we can barely imagine. The cosmos seldom acts on human timescales alone. Even a catastrophe, once it settles into a world, becomes an environment. If we continue to follow the thought to its most distant horizon, the stopped Earth becomes less a disaster scene and more a different planet wearing the memory of our own. There would still be children born beneath its altered sky, still animals tracing the safe margins of land and sea, still storms, though not our storms, still winters and summers of a kind, though stretched and rewritten by the year-long day, still rivers, though following changed coasts, still mountains, though looked at by different eyes. The planet would not end, it would diverge, and that may be the strangest part of all. So many of our fears imagine finality, a sharp edge beyond which there is nothing left to say. But Earth history is full of thresholds after which new stories begin. Mass extinctions are terrible, yet the rock record after them is not empty. It fills with survivors, experiments, radiations, delays, losses, and returns. Continents break and join, climates swing, seas rise and fall, ice advances and retreats, and life answers each upheaval not with perfection, but with persistence. The stopped Earth would be no different in principle. It would simply ask for persistence under conditions far beyond anything our species has known. There is another quiet consequence worth lingering over before the thought is allowed to fade. The moon would still be there. It would still orbit the Earth, and its gravity would still tug at the seas. Tides would not vanish. But tides, as coastlines once knew them, would be changed by the loss of rapid rotation and by the remade distribution of water. Lunar rhythm would continue inside a planetary body that no longer answered with its old daily turn. Estuaries, tidal flats, and shallow coasts that once lived by that regular breathing would now feel the moon through a world already transformed. The sky of the dark side would become both ancient and newly important. Modern people rarely know the stars with practical intimacy. Yet, under months of darkness, where ordinary dawn no longer returned on time, constellations could become useful again. Their slow changes through the year would help reveal the planet's continued journey around the sun. Astronomy, one of humanity's oldest sciences, would return to daily relevance. The heavens would once again become a clock, not because they had changed, but because the earth beneath them had. That would alter the meaning of history itself. The first calendars were not abstract systems placed upon a neutral world. They were answers to the sky, to floods, migrations, planting times, and the changing height of the sun. On a stopped Earth, surviving societies would need a different historical rhythm, one less tied to ordinary days and more tied to long passages of light and dark, to the movement of the twilight margin, to the reopening of a root, to the season when a sheltered valley still produced food. The old 24-hour world might begin to feel almost mythical, not because its evidence had vanished, but because its regularity had become difficult to imagine. That is one reason this thought experiment feels larger than a simple disaster. It does not only show us how vulnerable life would be, it shows us how supported life already is. Stability is easy to mistake for dullness, yet a repeating pattern can be extraordinary. The cooling after sunset, the return of morning, the daily exchange between light and darkness, the way bodies, weather, coastlines, and ocean life all lean on the same turning world. These are repetitions, yes, but repetitions of a very rare success. There are echoes of that truth in the geological past. Earth has known impact winters, greenhouse ages, vast glaciations, extinctions, and changing seas. But through all of those upheavals, one deep rhythm remained. The planet kept turning. Day and night continued to trade places. The atmosphere and oceans continued to respond to that turning. Life could collapse and still recover because the background clock of the Earth endured. The stopped Earth asks what happens when that clock is taken away. The answer is not only ruin, it is understanding. It reveals how many things depend on hidden regularity. A reef depends on light, current, chemistry, and time. A bird depends on wind, season, and magnetic orientation. A seed depends on darkness as much as light. A sleeping child depends on evening without needing to know why. Civilizations with mathematics, medicine, and satellites still rely on a rotating planet whose ordinary fidelity they did not create. We call that nature, partly because it arrives before us and continues beneath us, holding together systems too vast to notice unless we imagine them broken. And perhaps that is the final image worth keeping, not the violence of the stop itself, but the contrast it creates, a bright half and a dark half, heat without relief, cold without dawn, and between them, a narrow, migrating world where life waits, adjusts, and persists. It is an image that turns the whole planet into a lesson in balance. Too much light is a problem. Too little light is a problem. What life seems to love whenever it can is the moderated place, the alternating place, the place where extremes arrive but do not remain forever.
That middle condition is what the spinning Earth offers almost everywhere in one form or another. Not perfect comfort, certainly. Deserts are harsh, polar winters are long, storm belts can be violent. But even these extremes are set within a larger rhythm that keeps moving, keeps redistributing, keeps refusing to let one condition rule forever. Rotation is not the only reason for that generosity, but it is one of the deepest. By carrying every region through light and darkness, by helping stir air and sea, by sustaining the cadence of exposure and rest, it keeps the planet from hardening completely into one fate. There is a tenderness in that realization, though not a sentimental one. It is the calm recognition that to live on Earth is to be carried by systems we did not build and usually do not feel. We do not maintain the spin. We do not restart the dawn each morning. We do not direct the broad paths of wind over the ocean. Yet our meals, migrations, harvests, bodies, and dreams all depend on those background fidelities. The point of imagining them lost is not to dwell in fear. It is to make the invisible visible for a moment, to feel the hidden architecture of ordinary life, and then to let that knowledge soften into appreciation.
The spinning of the Earth is one of those unseen structures. It supports everything from coral reefs to sleeping rooms. It is one of the great, quiet kindnesses of the planet, so constant that most of the time it feels less like motion than like stillness itself. It is easy to love the dramatic Earth of storms, volcanoes, and ice ages. It is harder, and perhaps wiser, to love the ordinary Earth of repeated mornings, of predictable shadows, of nightly cooling, of tides that keep their appointments, of bodies that can trust the dark to return again. The thought experiment restores that quieter wonder. Perhaps that is the final gift of questions like this one. They do not merely frighten, they restore scale. They return wonder to things so familiar we mistake them for background. A sunrise is not only beautiful, it is evidence of a turning planet. A breeze is not only weather, it is part of a circulation written by rotation, heat, and geography. The steady cycle of waking and sleep in a living body is not merely habit, it is an ancient conversation between biology and a moving sky. To imagine the loss of these patterns is to see, more clearly, what they are. So the mind drifts back, slowly, from the speculative Earth of long light and long darkness to the real one beneath us. The real Earth, with its ordinary hours, its faithful alternation of brightness and shade, its weather maps shaped by invisible curves, its oceans carrying heat across familiar names, its coasts holding where they have learned to hold, its nights long enough for rest, and its days brief enough to survive. It is still a strange planet, of course. It always was. Strange that a sphere of stone and metal should wear seas. Strange that thin air should hold enough warmth for forests and whales and cities. Strange that creatures made of water and memory should look up, ask impossible questions, and feel calmer for having asked them. In the imagined world, somewhere along the twilight margin, the wind would still be moving over dark water. Farther away, on the bright side, long sunlight would wash a bare plain where an ocean once stood. On the cold side, ice would shine faintly beneath stars. The atmosphere would carry heat from one world into another. A narrow valley might hold green things under shelter. A distant coast might echo with the slow return of waves against a new shore. And above all of it, the sun would move with immense patience, almost too slowly to notice, while the altered earth continued around it in silence.
Then, even that world begins to recede. The harsh geometry softens. Fire becomes only warmth at a distance. Ice becomes only pale light. The great belts of air and sea relax into broad, quiet shapes. Continents fade into shadow. Clouds drift without urgency. The line between day and night becomes a gentle curve across a sleeping planet. Nothing rushes. Nothing demands. There is only motion on scales too large to feel, and the soft understanding that our own world is held together by such motion every day. And here, on the earth that still turns, the room is still, the air is calm, and the darkness arrives exactly when it should.